Today's lesson is graphing logarithms, and what we're going to start off with here is just a rough basic shape. So looking at the parent function of y is equal to log base a of x, a is going to be some constant bigger than 1. Now we know from domain range issues of previous lessons, this could be a fraction between 0 and 1. So for the purposes of it can be a fraction less than 1, as long as it's not negative, we're not going to be considering those with the type we're graphing. The type we're going to be graphing, that base right there is going to be a constant bigger than 1. So what happens here is all of your basic logarithmic graphs are going to start with a vertical asymptote at x is equal to 0. It's going to have a domain of x greater than 0. It's going to have a range of all real numbers. Now, sometimes this may appear like it kind of flattens out here, and it looks as though maybe, like in your particular graphing calculator screen, there might be a horizontal asymptote, but it never has a horizontal asymptote. You're always going to hit a range of all real numbers. And then the same basic function transformations that we always look at. If you add or subtract with the x, that'll slide it left or right in the opposite direction. Add or subtract out here. After the logarithmic part of the function is done, that'll move it up, down in the same direction. And putting a coefficient in front will make it a vertical stretching or compression of the graph. So with those basics noted, let's dive into some examples. All right, so we know the basic shape of this log graph is going to look like this. And that plus 7 is going to shift it 7 to the left. And that minus 1 is going to shift it 1 down. So we have a good idea of what to expect when we type it in the calculator. Now, as far as what we can immediately identify without relying upon a calculator, we know that the vertical asymptote starts at x is equal to 0. If the graph is shifting 7 left, our vertical asymptote is going to be at x is equal to negative 7. We know the entire graph will be to the right of that asymptote, so the domain is negative 7 to infinity. The range of all our basic logarithmic graphs is all real numbers. None of them have horizontal asymptotes, although sometimes it may look like they do, they don't. All right, so going to y equals, clear that out. I am going to type this in using the log base feature of the calculator, which is underneath math. So this is base 2 of x plus 7 and minus 1. And hit graph. So we got roughly what we expected from going through this little procedure right here. As far as things to identify over here, we want to get the x and y intercept. Okay, we can get the y-intercept by just hitting trace, and typically your calculator defaults to tracing to x is equal to 0. Y-intercept is when x is 0, and the instructions are 2 decimal places, so about 1.81. So the y-intercept is at 0, 1.81. To get the x-intercept, we're going to go to second calculate, use the 0 feature. It's going to ask us those 3 questions, left bound, right bound, guess. And we get negative 5. All right, now we just want a couple points to flesh out this curve, make it reasonably accurate. I'm going to go to my table, auto, good. So at -6, we're at -1. And from there, we know it's going right to the asymptote, so there's nothing else we need there. Let's get a point between 0 and -5. Looks like -3, 1. That's a nice clean one. And let's get a point or two out here. Okay, 1, 2, that's a nice clean point. Any others? 9, 3. There we go. So that's more than enough. Get a decent curve here. Just looking like that. And like that. Okay. Now, what if you were asked to find x and y intercepts, and you were asked to do so without graphing technology, like just a regular scientific calculator? How would you handle it? So y is equal to log base 2, x plus 7, minus 1. So if we wanted to get the y-intercept, we let x equal 0. All right, so this particular calculator, if we were to do it without graphing, using the graphing features of it, we could still have access to log base. We do log base 2, 7, minus 1, and enter, there's your 1.81. Now, if you're using an older graphing calculator, just a basic scientific calculator, it probably doesn't have that log base feature. So you'd have to use the change of base formula. So you'd have to go log of 7 divided by log of 2. And that gets you the first part, and then subtract the 1, and there's your 1.81. Or you could do natural log of 7 divided by natural log of 2, and then subtract the 1. All right, what about getting the x-intercept? Well, x-intercept, y equals 0, so 0 is equal to log base 2, x plus 7 minus 1. To solve this equation, we're going to want to get the 1 over to the other side. Rewrite that exponentially. And we get x is equal to -5. Okay, another what if in terms of calculator limitations. What we're going to do is take this graph and I'm going to shift it up higher. So I'm going to go to y equals, and instead of a -1, I'm going to do like a +5, just to see what that looks like. I want to go higher than that to show you what I want to illustrate. I'll go like +7. All right, what happens very often with the graphing calculators is you lose that part of the graph that's coming down. So one of the things that you need to recognize as a wise user of the calculator is that this graph is heading down to -infinity here. It doesn't stop there. When you copy this onto paper, you need to show it with the arrow that it's continuing down. So if we wanted to find the x-intercept of this graph without seeing where that graph crosses the x-axis, we're going to be limited, and we may or may not be able to use that 0 function in the calc menu. So there are times where even if you can use a graphing calculator to find an x-intercept, you're not always going to be able to do so with the graphing feature. You may have to use this method. So that is one of the limitations that tends to happen with doing logs in a graphing calculator. Equals, clear this out. All right, we'll do one more example. All right, natural log of x plus 5 minus 2. Well, remember, natural log is log base e of x plus 5. In this case, x plus 5 minus 2. So we have our basic logarithmic graph like this. It's going to be shifted 5 to the left and 2 down. So that gives us a good idea of what to expect when we type it in our calculator screen. It also allows us to answer some of these features without necessarily doing a whole lot of work. So if this graph shifted 5 to the left, that means the vertical asymptote is that x is equal to negative 5. Draw that in. We know the entire graph will be to the right of that line, so the domain is negative 5 to infinity. All of our basic logarithmic graphs have a range of all real numbers without a horizontal asymptote. So in terms of things to identify here, you need to get the x-intercept, you need to get the y-intercept, you need to flesh out some points here. All right, let's go to the graphing calculator. Natural log, x plus 5, and minus 2. Graph. So it's roughly where we expect it to be. Again, that line keeps going down like this, or that curve. Just because you don't see it doesn't mean it's not there. It's just a limitation of the calculator. Trace. The y-intercept rather is going to be at negative 0.39. Right below the origin. In order to get the x-intercept, I'm going to use the 0 feature. Do the left bound, right bound guess. And we're about 2.39. And we'll go to our table, grab a couple more points. All right, so negative, anything good here? Negative 4, negative 2. 1, 2, 3, 4, 1, 2. And let's just get negative 2, negative 0.9. And we know that it's going right to the asymptote from here. So we don't need to get any points. We'll just get 1 or 2 points up here. So any clean ones we can grab? Not really. Let's go like 5.3. And we'll go out to like 10 and then 0.7. So that's looking pretty solid in terms of reasonably accurate graph. All right, let's take a look at the intercept thing. So if we wanted to get the intercepts by hand, or without advanced features of a calculator, in order to get the y-intercept, we're going to let x equal 0. Now the ln of 5 minus 2, that would be the exact y-intercept. And there are times where maybe you're asked for what is the exact y-intercept, in which case you leave your answer like that. In terms of a decimal approximation, ln of 5 minus 2, and there's your negative 0.39. Okay, to find x-intercept, y equals 0. So I'm going to bring this 2 over. Rewrite that exponentially. Bring over the 5. So the exact x-intercept would be e squared minus 5. So it's possible that you could be asked for what is the exact x-intercept for the graph, in which case you'd leave your answer like that. as a decimal approximation. Hopefully it matches the one we got before. 2.39. Let's double check that with what we got. 2.39, negative 0.39, same answer either way. And that's all I'm going to go over as far as class notes for today. There are 3 additional practice problems. Where'd the other side of the paper go? On the second page, there we go, of this worksheet. Okay, practice as many of those or as few of those as you feel you need to. I will post the solutions to those up in Google Classroom.